Welcome. In this video, we're going to be looking at the CCNA 2 Routing and Switching Essentials course, chapter number 1. Chapter number 1 is all about routing concepts. So in this chapter, we'll be starting to explore in a little more detail than previous courses exactly what's going on with routers, how they work, how they make some decisions, some of the different features that are available, etc., and kind of lay the groundwork for some additional and more advanced router configuration and network setups that we'll be doing in this course. So we want to fundamentally keep in mind that our idea here with networking is to allow devices and people to communicate, collaborate, and interact. So in order to do that, we need to make sure that we get traffic from source devices to destination devices. So chapter 1 is kind of focusing on how do we get traffic from devices on one network to devices on another network. So in order to do this, we need to have something that connects multiple networks together, and that's fundamentally what a router is. Routers are gateway devices that allow us to connect together multiple different networks. So we can do this by placing some interfaces of the router in one network and other interfaces in another network. In fact, realistically, like in this example here, this router is attached to multiple different networks. It's every interface on a router is in a separate network. It's in a different network from the other interfaces. So if you have a router like we have here in this branch office, we have a connection to one network on this side and a connection to one network on this side. A lot of times we use routers to connect together local area networks like this, or a group of different, like in this case we have 3 different local area networks, right? To a wide area network, right? A wide area network allows us to cross much greater distances. But routers can also be used just within local area networks. Certainly routing happens within local area networks. It turns out that we can actually do some routing on switches. And we can do that by having these types of devices here, different graphic, and that's a multi-layer switch, or an MLS. So we actually talk a lot more about multi-layer switching in the CCNP courses, because it is traditionally been a little bit more of an advanced topic. In the next revision to the CCNA, I expect that they'll be talking a little bit more about multi-layer switching in the CCNA. In fact, in this version of the CCNA, they do start to introduce that concept. So realize that exactly what a switch is and what a router is, there's a little bit of a gray area there because we started to build switches that have routers integrated into the switches. But when we're talking about routing, not just routers, but routing is just in order to move traffic from one network to another network, we need to have some routing that is taking place. One of the things to remember is really that routers, or devices that are doing routing, are really just computers. Okay? They're specialized computers. But inside of a router, you're going to find a CPU. You're going to find some memory and some permanent storage. So like RAM and basically a solid state drive. And then you'll also find an operating system. So the operating system that we're using is called Cisco IOS, right? The CPU is probably not going to be like an Intel CPU, but it might be a MIPS CPU or an ARM CPU or something like that. And then, of course, we'll have some RAM and storage, although much less than you would probably typically find on a PC. So all these kind of similar things that we have in a PC are going to have in a router. In fact, you can take a PC and you can turn it into a router. Now, it's not going to be the most efficient router because it's not going to have some of the specialized circuitry and components like content addressable memory or ternary content addressable memory like a router or a multi-layer switch will have, but it is going to be able to fundamentally route traffic from one network to another network. We just have to have multiple network cards in it and be running some software that can do the routing. Inside of like a Cisco router, we're going to find memory that includes random access memory for like the operating system, the configuration files that are running, the tables for routing and ARP, a packet buffer so that if information is arriving at the router faster than we can send it out, we can hold some packets temporarily. We'll find some ROM memory, some read-only memory for boot up instructions, diagnostic software, things like that. We'll find what's called non-volatile random access memory, or NVRAM, which is where we can store our startup configuration file. So it's stuff that it's like RAM, but it will last through a reboot. Even if the router gets switched off, the memory still retains its information. It's basically like an older version of flash memory. Now, in newer routers, as flash memory's gotten less expensive and so on, in some cases the NVRAM is really just a small piece of the flash memory. Okay, and then of course we have flash memory for the iOS software files, system files, etc. Physically looking at the router, right? We've looked at routers and switches a little bit in previous courses. But looking at the router, we have some places for our solid-state flash memory. Okay, some in like the Cisco 1941s, like we're looking at here, they're accessible from the outside, and there's just compact flash cards that can go into these flash card storage slots. We also have two what are called HWIC slots, or EHWIC slots. One is right here and one is right here. This one is a double wide one, so we can put in larger cards, but it's still just technically a single slot. And those are typically going to be used for wide area network interfaces or adding additional types of interfaces. In the routers in our lab, we've got a T1 card in this EHWIC 0 slot, and we use that for setting up our serial ports. But you can also get additional Ethernet ports that go into these. You can get wireless modules and serial modules and lots of other types of additional ports that you can add to the router as well. We have some console ports, like a RJ45 console port and a mini USB console port. For programming, we have an aux port for remote access to the router over like a dial-up line or a cellular connection, so that we can get remote access to the router if our network connection goes down and we can't be physically at the router. We can have some Ethernet connections, gigabit Ethernet connections in this case, that are built in, and then some USB ports for attaching like flash drives so we can save our configuration onto flash memory. So this really is just got all of the same components that we might have in a PC. They move on to talking a little bit about how routers actually can move traffic from one network to another network. And there's three main ways that this is done. Now, we call these the different types of switching, but they really are routing. Okay, we're just talking about switching traffic from one network to another network. For historical reasons, there's some confusion in the terminology. But we're talking about routing here, even though you'll hear us refer to these processes as switching. So the first way that we can do this, that we can move traffic from one network to another network, is to run some software. And that software can look at all the traffic that's coming in. It can look at the destination IP address, look that up in a routing table, and figure out what network it needs to go on to next and what the next hop on that network is going to be, and then create a new layer 2 frame that we can put around the layer 3 packet with that next hop destination on it and send it out on its way. We can do it all in software. Okay? And that's called process switching. The problem with process switching is that it means every packet needs to be read by the CPU, modified, rewritten, a new layer 2 frame created for it, and then sent on its way, all done by software on the CPU. Now, software is fast, much faster than a human could be, but it's not the fastest thing we can do. It certainly processes things much more slowly than we actually can receive them. So if we have a gigabit Ethernet interface, it means that our router will operate at much lower speeds than gigabit. So that's the disadvantage with process switching. So eventually, Cisco came up with something called fast switching. And fast switching is where the first packet that comes in, because a lot of times we're sending more than one packet at a time from a certain source to a certain destination. So with fast switching, the first packet comes in, it gets routed by software from one network to the next, and we figure out what the correct next destination network is, or destination hop is for the traffic, what's the next router it's going to go to, or the next network it's going to go on to. And then we store that information into some special cache memory. Cache memory can be, very fast memory that the router can look at without using software, packets that come in, and if they match that source and destination IP address, the router no longer has to look it up manually in software algorithmically. It can just look in memory and go, oh, if it's going to this destination IP address, this is the next hop it needs to go to, and it can send it on its way. So after we process the first packet in software, we can store kind of those settings in a much faster memory that we can recall and make the changes to following packets very, very quickly. We call that fast forward cache. It does mean that if we're only sending one packet, it's going to be a slower process, just like the process switching was. But if we're sending multiple packets to the same destination, which is oftentimes the case, right? If we're sending a large file or something like that, we're going to be sending multiple packets. Then we can treat the packets after the first one in a much, much faster way because we can temporarily store that information about how to send the traffic on to its next hop. Now, better than that is something called Cisco Express Forwarding. So this is usually how we do things today. There's sometimes some reasons where we need to do fast switching or process switching, but Cisco Express Forwarding, we don't even send the first packet up to the CPU. So what do? Well, the CPU basically pre-computes what the next hop address is for any given destination network address. And so it pre-computes that and then stores it into its cache memory, which in this case we call a FIB, forwarding information base, and adjacency table on the device. So when we pre-compute this and store that in, that means as soon as the first packet comes in, we already can look up in that fast memory how to or where to send the traffic next. This special memory that's used for this is called CAM, Content Addressable Memory, and Ternary Content Addressable Memory, or TCAM. We go into a lot more detail about how these different types of memory work and why we can do things in much, much faster ways with fast switching and Cisco Express Forwarding than we can with process switching in CCNP level classes. But for now, you just need to understand basically these three different types of routing that can take place: process switching, fast switching, and Cisco Express Forwarding, and a little bit about what the advantages of each one of them are. So those are our three different methods for forwarding packets. Now, as you might have guessed, we're going to be doing a lot more work in the command line on the routers and switches in this class, because this class is all about learning how to configure and set up routers and switches to get them to move traffic amongst themselves. So one of the things that is useful to be able to do is to look at information that the router and switch is providing when you're doing some troubleshooting. We typically do that using show commands. So it's pretty common that we'll do something like a show running -config or a show interfaces or something like that. But a lot of these commands give us much more output than we really need. So, for example, the show running config can show you several screens of output with even a relatively basic configuration. And if you have a more complex configuration, you can have many, many, many screens that you have to scroll through in order to find what you're looking for. Luckily, we can use some special commands on routers and switches to filter the output that we're getting to only see certain information. So the first one of these, it looks like this. So here's a show running config command, but then you'll see after it we've put this character. This is a vertical pipe or a pipe. Exactly where this character is located on your keyboard varies a little bit from one keyboard manufacturer to another, but on many keyboards it's found on the same key as the backslash key located above the enter key. Sometimes it's in the far upper left corner above the tab key and so on, but in this case you'll find it, and on most modern keyboards that I've seen, it's oftentimes for PCs, is usually above the enter key. Now, the pipe character it shows up on the screen as a straight vertical line. On your keyboard, it oftentimes looks more like a colon, except that it has two separate short straight vertical lines, but they're not dots like a colon. They're straight lines. So that's the pipe. And if you've taken a Linux class before, you'll be familiar with this. But basically, the pipe in computer programming is used to take the output of one command, like show running config, and we pipe it into another command, in this case, section line VTY. So we're taking the output of one command and we're processing it with another command before we display it. So in this case, what this command is going to do is it's going to show the running config, but then the router is going to filter out only the line VTY section of the configuration. Okay, so here you have that VTY line section. So it's the section that starts with line VTY, and then all of the indented lines below that kind of belong inside of that line VTY. So that's a useful command. It can show us one section, typically of a running configuration, at a time. Another one we can use, again, you'll see here we're doing it again with the pipe. And this time we're going to, instead of just a show IP interface brief, which would give us an output that looks like this, if we only want to see interfaces that are up, right? So that would be these three, and not this one, and not this one. If we only want to see interfaces that are up, we can take the show IP interface brief command, and we can again pipe it, but this time to the include up. What this means, it'll only show us lines of text that include the word up in the line. So up has to appear somewhere in the line. This is not like super fancy. If the name of the interface over here included UP somewhere in it, it would show the line whether it was up or down. But we know that typically these interface names don't contain the letters UP, so it's going to show us ones where the status or the protocol is in the up state. So when we run this command, show IP interface brief pipe to include up, then we get only these three lines, which are these three lines right here. Notice we don't get this heading line up at the top, right? So we just have to know what these columns are because we work with the routers and switches on a regular basis. Because that line up at the top does not contain the word up anywhere. So that one gets filtered out too, right? It's not super complex. It's not super fancy, okay? But it does allow us to limit the output. Now, if we only have a few devices or a few interfaces on our device, like here, we only have a few, it really isn't particularly useful, right? You can view all those pretty easily. But if you have a very large router or switch with hundreds or thousands of interfaces on it, you could have multiple pages of interfaces that you would otherwise have to look through. Well, this way we can include specific lines only, okay? So we could filter for the word up, we could filter for the word down, we could filter for the word gigabit Ethernet or something like that and see only the gigabit Ethernet interfaces. So lots of useful things we can do with that command. Similarly, we can also use the exclude command. So in this case, if we want to exclude ones where we don't have IP addresses set on the interfaces, we could say exclude unassigned, and then any line that has the word unassigned in it will not show up in the output, right? So but kind of the opposite of include. Include, the line has to include what we say, and exclude, it cannot include what we say. So this time you'll see that we do have that header line because the header line doesn't have the word unassigned in it. The only ones that have the word unassigned in it are these two, and so they will not appear in the output. We also can use, like a show command, like in this case, show IP route, but we can do it with a running config or anything else as well. And we can pipe it to the begin command. Well, the begin command says, find in the first time that some word, in this case the word gateway, appears in the output, and then start showing the text from that point on. So in the show IP route command, this is the first line that contains the word gateway. So we're seeing that line and everything that comes after it. Okay? So that's the begin command. So those are a few of the commands that are really useful for limiting exactly what details you want to see from a router or switch. And they give you some flexibility so that you don't have to scroll through pages and pages of stuff. You can kind of jump more quickly to the exact information that you are looking for. Another thing is that you may have learned when you're using a router or switch, if you press the up arrow on your router or switch, you can go back to a previous command that you have entered on that router or switch. So it makes it much faster. Rather than retyping a whole line, you can just, if you made a mistake or something like that, you get a new command prompt, you press the up arrow, and it will show you the command that you previously typed. If you press the up arrow again, it'll go back another line. Press the up arrow again, it'll go back another line. By default, it will keep the last 10 lines that you have used. And it will store those in what's called a history buffer. You can view those last 10 lines that you have used using the show history command. So the show history command will show you the last, in this case, 10 lines that we've used. You can tell the router to save more than 10 lines if you want with the terminal history size command. So if you do terminal history size 200, now it will remember the last 200 commands that you have typed in. And when you do show history, it'll show you all of those, or you can press the up arrow up to 200 times to see the last 10 lines. So that is something useful as well. Of course, it does take more memory the more commands you want to store, so you need to make sure that your router or switch has enough memory in order to increase that terminal history size. Most of the recent routers and switches have no problem storing a couple hundred commands, but older devices did, and so that's why the default is set to only the last 10 commands. So that's another useful thing, just a little tip and trick when you are configuring routers and switches. Okay, so how about the actual process of routing? So this is something we've talked about before in the CCNA 1 course, is kind of how this process of routing works. But let's say we want to send some traffic from PC1 to PC2. Now these are on two different networks, and they're not just going through one router, but in this case, you have to go through 4 routers to get from PC1 to PC2. So exactly what happens? Well, PC1 has the data up in an application, right? So it's starting up at layer 7 of the OSI model. And it gets encapsulated. It gets put into a TCP or a UDP segment. It gets segment numbered if it's TCP and all of that stuff. It gets an IP address, so it gets a source and destination IP address. It's got a port number, etc. Gets put into maybe like an Ethernet frame. Gets put out on the wire, on the physical connection, and it'll come out of PC1. Now, PC1 is going to do some figuring, and the operating system on the device is going to realize, hey, I need to send this traffic to a different network. So in order to get to a different network, I know I need to send it to a default gateway. Well, it still puts the real IP address as the destination IP address at layer 3, but at layer 2, instead of the actual MAC address of PC2, it's going to put at layer 2 the MAC address of the default gateway. So it figures out using ARP, etc., what the MAC address for its default gateway is. In this case, that's going to be the address of router 1's Fast Ethernet 00 interface, which is 192.168.1.1. It doesn't do anything more with that IP address. That IP address will never appear in any of these packets, but the MAC address for that interface will appear in the layer 2 header as the destination MAC address. Okay, so then it puts it out onto the wire, and it gets collected at router 1 on that FA00 interface. When it goes into router 1 strips off the layer 1 information. It strips off the layer 2 information. Don't need that anymore. And then it looks at the layer 3 information. It doesn't change too much about layer 3. It is going to reduce the time to live value by 1 in the layer 3 information, but it's not going to change the source and destination IP address at all. It figures out, okay, here's where this final destination for this packet is. The address is 192.168.4.10, right? Well, I'm not connected to that network, but I'm going to look up in my routing table and see if I'm connected to anyone else that is closer to that network. And it turns out, yes, I am. I'm connected to router 2. Router 2 says it knows how to get to the 192.168.4.0 network. So it's going to put a new layer 2 frame on that same layer 3 packet. And that layer 2 frame is now going to have the destination MAC address for router 2. So it gets sent out over the wire, it goes to router 2. Router 2 does the same thing. It looks to see, well, am I connected to 192.168.4.0? No. But in my routing table, it says, in order to reach 192.168.4.0, I need to send it to router 3. And router 3's IP address is 192.168.3.2. So I'm going to figure out the MAC address for 192.168.3.2, and then I'm going to send it out over the wire to router 3. Router 3 looks at it again, and now it goes, oh yeah, router 3, I'm attached to the 192.168.4.0 network. So when I put my new layer 2 envelope on the outside of this packet, I'm going to set the destination MAC address to the actual MAC address of PC2 that I have figured out using ARP, okay? And it sends it out over the network, and then finally PC2 gets it. It takes off all the information. It keeps working its way all the way back up to whatever application requested that information on layer 7. So that's kind of how the process works. And this is why we call routers layer 3 devices, because the packet only goes up to layer 3 every time that it goes through a router. Every time it goes through a switch, the packet only goes up to layer 2. So that's why we call switches layer 2 devices. So that is kind of what our overall routing process looks like as the traffic moves from PC1 to PC2. Now that's something we talked about in CCNA 1. So just a bit of review about that before we dive into a little more detail about how the routers actually make those decisions about where to send it next. Okay, so what happens at a router? Well, when a packet shows up at a router, the router takes a look at that packet and it says, what's the destination IP address for this packet? It figures out what the destination IP address is for that packet by looking at the layer 3 destination information. And if it's not for the router itself, then it needs to figure out, well, I need to hand this off to somebody else, either to its final destination or to the next router in the chain. So it's going to look in something called its routing table. And what it's looking for is what matches the destination IP address. Does it match the subnet? First of all, the router looks, are there any directly connected interfaces attached to that network address? So if the destination IP address is on a network that the router is directly attached to, the router knows I'm the last stop before this goes to its final destination. So it's going to then look in its ARP cache if it's using a Ethernet type network, which is most likely what you'll have. and it'll figure out what the MAC address is and forward to that particular host, right, by putting that MAC address in as the destination MAC address. If the router looks through all its directly connected networks and it goes, nope, none of the directly connected networks are for this particular subnet that this packet is trying to go to, then the next thing that it will do is it'll check, oh, okay, so I'm not directly connected to it, but do I know how to get to this network? Do I have an entry for this network in my routing table? If yes, then I look up in the routing table, well, in order to get to that network, what's the next router this traffic needs to go to? And I will change the layer 2 information on it so that it goes to that network, next network that the traffic needs to go through, either out of a particular interface or to a particular IP address of the next hop router. If we don't have an entry in our routing table for the remote network, we check one more thing. We have something in routers that we can program called a gateway of last resort. A gateway of last resort is like a default route or a default gateway on your PC. It basically says for a router, hey, if I have no idea where this particular network is, if I don't know how to get here, any traffic, I don't know exactly how to send it to its destination network, I have a particular router that I'm going to send all of that traffic to. So this is how, like, your home router, rather than having the entire copy of the internet routing table in your home router, you're not going to do that. It would take up way too much space in your home router, and all the stuff is going to go to your ISP anyway, right? So instead, your home router just has a gateway of last resort. And your home router basically says, if it's going to a network that I'm not directly connected to, if it's not a network I know how to get to, if it's some random network on the internet, for example, I'm going to send it all to this particular router at my internet service provider. So if we have a gateway of last resort programmed, then we will send it to that next gateway, that next router. If we don't have a gateway of last resort, then the router is like, well, too bad, I have no idea where to send this packet, so I am just going to throw this packet in the trash. Okay, so that is the routing decision-making process. Now, every router makes these decisions independently. Okay, so it's not like the first router that sees the packet figures out exactly what the whole path through the network is going to be. It doesn't know all the routers the packet is going to go through. It doesn't know, in many cases, how many routers the packet is going to go through. It just knows where to send that traffic for that network next. It knows what router traffic for that network should go to next. How does a router figure this out? Well, we can either manually program it into the routers, or we can have the routers exchange information automatically and figure out on their own what the best path through the network is. However, what does the best path through a network really mean? Well, we have a couple of different ways that we can immediately come to mind to think about this. The simplest way of determining the best path is, of course, the shortest path. So what we can do is we can count how many routers the traffic will go through to get to its destination, and we call that hop count, right? So router 1, if traffic is going from PC 1 to PC 2, when the traffic gets to router 1, it has to decide, should the traffic go to router 2, to router 3, to PC 2, or should the traffic go from router 1 to router 3 to PC 2? So router 1, it could send the traffic out of either interface. It could send the traffic out of this interface, let's do this interface, or this interface. But And it could still get to PC2, right? Because both of those can eventually get to PC2. But which one is better? Okay. Well, if we're doing it by hop count, that's the number of routers the traffic's going to go through. So from router 1, not including router 1, traffic going through router 3 over the green link to PC2 is going to go through one more router. Traffic going over the yellow link from router 1 to router 2 is going to go through router 2 and router 3. So it's going to go through two routers if it goes that way. So if we're using hop count, the yellow path takes 2 hops and the green path takes 1 hop. So the green path is better, right? Well, if we're just basing our routing decision on hop count, then yes, the green path is better. However, what we're not taking into account is the speed of the interfaces. So notice the connection between router 1 and router 3 is 56 kilobits per second. The connection between router 1 and router 2 is a T1, so that's 1.5 megabits per second. And router 2 to router 3 is also a T1, 1.5 megabits per second. So that's where things get tricky, because the green path is going to be the shortest path, but the yellow path is probably a faster path because the connections between the routers are faster. So if we tell the routers to program themselves and find a route through this network, which path are they going to choose? The answer is it depends. It depends on the routing protocol that we use. That's the standard that the routers are using to communicate back and forth about different networks that they're attached to. If we're using a simple routing protocol like RIP, which we'll talk about more later in the course, it uses hop count. So RIP will choose from the green path to send the traffic. If we're using something more complex like EIGRP or OSPF, which we'll also talk about later in the course, they use bandwidth as part of the calculation. They use a more complex thing. It's not just bandwidth or hop count. It's a combination of hop count, bandwidth, delay, latency, all kinds of other stuff that goes into mathematical algorithms, and they come out with a number. But they take bandwidth into account. So EIGRP or OSPF are more likely to choose the yellow path. So you do have to realize that it's not so simple to figure out what the best path through a network is. Because if we only use bandwidth or we only use hop count, we'll end up with some routes that are suboptimal. They'll get traffic to the destination, but potentially not as fast as we otherwise would get that traffic to its destination. Now, if we can have routes that go into routers and take a lot of different things into account, like if RIP is only taking into account hop count, but EIGRP and OSPF include things like bandwidth and so on, and maybe we have, for some reason, we want to manually override the router and say traffic to this destination network should always go out of this interface, and I don't want you to take into account anything. That would be like what we call a static route or a manual route. We want that to take priority over everything. And of course, if a router is directly connected to a network, that should be like, don't send it out of any other interfaces, send it directly onto the destination network if your router is directly connected to that destination network. Well, how can we compare these things? That's where this thing called administrative distance comes into play. So administrative distance is a number that allows routers to compare different ways that they have learned about different networks. So routers can be directly connected to a network. We can manually or statically configure a route. There's these things called EIGRP summary routes, BGP routes, regular EIGRP routes, IGRP routes, OSPF, IS, RIP. Most of these are different protocols that the router can use to learn about routes. Okay. In fact, all of these are different protocols the router can use to learn about routes. Static routes are ones that we manually set, and connected networks are ones, obviously, that the router is directly attached to. So because all of these are going to generate these things called metrics, which are how we compare the routes, but the numbers between them are not comparable, we have to assign this thing called an administrative distance. These are default administrative distances. So for each one of these different ways the router can learn about routes, it has an administrative distance associated with it. If you don't like the order that Cisco puts them in, you can change these numbers to change the order. But these are the defaults. So if we're directly connected to a network, that has an administrative distance of 0. So that is the way you will always reach out to transmit the packet directly onto a connected network, because it has such a low administrative distance. If you've manually programmed a destination network, you will have an administrative distance of 1. Now, that's a very low number. It's the lowest number other than 0 on the chart. So if you have an administrative distance of 1 for static routes, that means you will always follow the static route if it's not a directly connected network. Then all of these other protocols are ordered all the way until we get to internal BGP, which has an administrative distance of 200. So anytime we learn about a route with internal EIGRP, we have those routes have an internal or have an administrative distance of 90. If we learn about the same network using RIP, that has an administrative distance of 120. So if we learn about the same network with 2 different protocols, we'll always prefer the EIGRP way that we learned, what the next hop is with EIGRP, over whatever RIP tells us. So that's what those administrative distances allow us to do. They allow us to compare these different ways that we learn about routes. Now, in Chapter 1, they do talk a little bit about some actual routing, right? And they talk mostly about the 2 different kinds of routing, static routing and dynamic routing. So static routing is where we set manually where we want traffic to go. So imagine we have a network like this, right? We have router 1 over here, we have router 2 over here, okay? And right now we're working on router 1. And we want to say, hey, router 1, you are directly connected to 3 different networks. You're connected to this network, and this network here. If you do not, if you receive some traffic that is not for one of those 3 networks, let's say you receive traffic for this network or for this network, or any other network, no matter what, router 1 should forward, if it's not directly connected to it, it should forward the traffic to router 2. Okay, we can set a gateway of last resort. We talked about gateway of last resorts before. In this case, we have manually configured a static route with this IP route command, and we've said IP route, and then this would be the network address, and this would be the mask. So if we put in all zeros for the network address and mask, we can then specify either an exit interface or the next hop IP address. So in this case, we're specifying an exit interface of serial 000 because we want all traffic that the router doesn't know. So if this routing table doesn't have the network address in it for destination traffic, it's going to get sent out of serial 000. Okay, because we have programmed this default route in right here and said, hey, if you don't know where the traffic should go, send it to serial 000. And that'll send it on to router 2. So that's one way to do a static route. That programs that default gateway, basically. Another way of setting up a static route is for a specific network. Right? So if we have a specific network like 10, even though this arrow is pointing up here at router 1, that's not accurate. We're really working on router 2 this time. So notice router 2. If we want to program router 2, hey, if you get traffic for the 192.168.10.0/24 network, I want you to send that traffic to router 1. Or out the serial 000 interface. I can do that with this command right here. On router 2, I can say IP route, then I put the network address, 192.168.10.0, then I put the mask, 255.255.255.0, because it's a /24, okay? And then I can say the exit interface. serial 000. So now router 2, any traffic that it doesn't, or any traffic that it has for this particular network, it's going to send out of the serial 000 interface onto router 1. Okay. Now, similarly, we can router, still working on router 2. Set up 192.168.11.0, this network down here. Again, a /24. This time, though, instead of an exit interface, and this is actually a little more common what you'll see, I think, instead of an exit interface is you put the next hop IP address. So that's an IP address that is on a network router 2 is already connected to. So that would be this address right here on router 1, 225. So we're saying to reach 192.168.11.0 from router 2 /24, send it to router 1. And then router 1 will look in its routing table and it'll figure out, oh, I'm directly connected to that network. Okay, so I can make that connection directly out of my gigabit 01 interface. Now you'll see if you look at the routing table on router 2, if you do a show IP route command, you'll see that these two routes get entered here in the routing table. And so that's how the router knows how to reach those networks. That's what the router 2 is looking at when PC4, for example, sends some traffic to router 2 that needs to go on to PC2, right? The router's going to find this route right here, and then it's going to say, oh, I need to send this traffic next to router 1. Okay, so that is how we can enter a static route. They've got some practice examples here for you about setting up static routes. Don't worry, the next chapter in the course, chapter 2, is going to be in much more detail about static routing. This is just kind of an overview for you how it works in chapter 1. And basically the same type of thing works with IPv6. Okay, I'm not going to go through explaining that whole thing, but the same type of thing works for IPv6. The alternative to static routing is where we would manually program in our networks. And that works okay in a small network or if we need to manually override something for some reason. But if you can imagine, if you're in charge of a large corporate network and you have, hundreds of different subnets, you're not going to go into every router, because in order for traffic to flow through the whole network, every router needs to know about every network. So you're not going to go into all of your routers and program in all of your networks and where they should go next. That's just crazy. So you're probably going to use something called dynamic routing, and that's where the routers can exchange information automatically about networks they're attached to and networks they know how to get to but might not be attached to. And you're going to do that using some kind of dynamic routing protocol. That could be a protocol, as I mentioned, like RIP or EIGRP or OSPF. Okay, so those are a few examples, but there are other ones available as well, and they all have their own advantages and disadvantages. We're going to start to talk more about dynamic routing in Chapter 3 of this course, and then we'll move on a little bit, and in future courses, we're going to talk about some of the different dynamic routing protocols and what the advantages and disadvantages of those are and how to configure each one of the different protocols. So that'll be coming up in future courses, but we'll talk a lot more about the general concept of dynamic routing once we get to Chapter 3. But for now, really, it's mostly about knowing dynamic routing is something that allows routers to exchange information amongst themselves using a routing protocol like EIGRP or RIP. And if you look at the routing table in a router that is setting up or is set up with a dynamic routing protocol, you'll see instead of a manual configured route, you'll see a letter here that indicates what routing protocol taught the router about that particular network. You'll also see some stuff here that includes like the metric, like how far away the network is. In this case, they're using EIGRP, so we have an administrative distance of 90, and this number here, this metric, would include the bandwidth and a bunch of other features about, how far away that network is, basically. Okay? And then, of course, the next hop address as well. So, like I said, we'll get to more about some of the dynamic and static routing as we move further into this course and future courses. I think we'll leave things there for now with Chapter 1. Be sure to ask any questions that you have about the content, and we will continue on and see you again soon.